So today I would like to tell you something concerning one last topic regarding the, let's say, behavior of Bloch electrons and their interaction with the external fields. One point that we considered using both the Drude model, the Sommerfeld model, was the interaction with the electromagnetic waves. So the interaction between the electrons within the solid and the electromagnetic waves that one applies to the system. In the case of the Drude model, we saw that the dielectric constant had a structure that was related to the dielectric constant, relative dielectric constant, that had this structure in the Drude model. And what we saw was that due to this structure of the relative dielectric constant, the behavior of the different metals was nearly the same, since just the electronic density enters in the definition of the value of the plasma frequency. So due to that, the structure of the absorption spectrum is nearly always the same. What changes is just the plasma wavelength. That means the wavelength that separates the regime where you have transparency from the regime where you have absorption. So nearly all the metals display exactly the same behavior. So it was not possible to explain why some metals have a color and some other metals do not have any color, or have the typical bright structure that you observe, for instance, in aluminum, silver, and so on. Then when we consider the Sommerfeld picture, then Sommerfeld introduced the concept of electronic level. So in principle, one may expect to, let's say, observe an absorption due to the fact that we have disposed electronic levels, and then the electromagnetic waves or photons may induce a transition from one level to another level. But as we will see in a while, that was not possible for the Sommerfeld picture. So what I would like to discuss with you now is how may we describe the interaction between the solid, the metal, and the photons, considering the case of Bloch electrons. So using the Bloch picture, I would like to comment about the electron, photon interaction. So in general, if you have a process of interaction that involves the electron and the photon, what you expect is to apply both conservation of energy and, in general, the conservation of momentum. But if we consider a solid where we have Bloch electrons, in this case, we have to consider the fact that the, let's say, ionic potential is not characterized by an arbitrary translational invariance. So due to that, if this interaction between the electron and photon takes place within the lattice, within the solid, then we may not apply directly the momentum conservation, as that is not observed in this case. So the equation, the first equation that we may write is the energy conservation. So in this case, we expect that if the electron, for instance, absorbs a photon, then the final energy of the electron is equal to the initial energy of the electron plus the energy of the absorbed photon. So in this case, the initial level is characterized by a value of the index n and a value of the wave vector k. The final level will be characterized by a different value in principle of the index n prime, and a different value also of the crystal momentum k prime. So the first equation, this one regards again energy conservation. Then when we consider the semi-classical equation of motion, we notice that, let's say, the term semi-classical meant that the effect of the lattice on the electron was considered through the energy dependence on the crystal momentum, while the role of that was of the, let's say, the role of momentum in the classical or Sommerfeld picture was obtained by the crystal momentum. So what we expect is that in this equation, the momentum will not directly appear due to the fact that we have no momentum conservation. But what we may expect is that as the role of momentum in the Bloch electrons dynamics is assumed by the crystal momentum, we may expect that a conservation law will be still obtained, but in this case, what we expect to have here is not the actual momentum of the electron, but the crystal momentum. So in that, so in this situation, we may write that the final value of the crystal momentum of the electron will be equal to the initial momentum of the electron plus the momentum of the photon, yes, and I call Q the wave vector of the photon. So here we have a combination of, let's say, an actual momentum with the crystal momentum. So from the point of view of the electron, we have the crystal momentum. From the point of view of the photon, we have the momentum of the photon. So here we have a combination between what has the role of a momentum in the Bloch electron models, that is actually the crystal momentum, and the actual momentum again of the electron. Then one last thing that one has to consider in this equation is the following. Since we are working in the reciprocal space, when we consider the crystal momentum of the electron, the actual value of the crystal momentum is, let's say, what is important to know is the value of the crystal momentum of the electron within the first Brillouin zone, due to the fact that we have a periodicity of the properties of the electrons in the solid. In particular, we have a periodicity of the energy. So if, just to make an example, if I consider a cubic lattice, and here, so I have that that the first Brillouin zone has again a cubic structure. Then when you apply a conservation law that is similar to this one here, if for instance you consider this SK, then due to the application of that conservation law, you sum another wave vector that is in this case is Q, and the final point is out of the first Brillouin zone. So in this case, K prime should be like that. So in this case, K prime is out of the first Brillouin zone. So the idea is, if we consider that the K values are just within the first Brillouin zone, so we use the first Brillouin zone as a volume where all the possible electronic wave vectors can be described and represented, then we have to handle also this situation where the final momentum may be out of the first Brillouin zone. In this case, we may explain the periodicity of the problem. So one point that is here out of the zone is equivalent to another point here within the zone. To make these 2 points equivalent with each other, what we just need is to make a translation from, in this case, the second zone to the first one using a vector belonging to the reciprocal lattice. So in this case, the idea is to include in the conservation law a vector G belonging to the reciprocal lattice such that the final value of K prime is not out of the first Brillouin zone, but is within the first Brillouin zone. So the typical, let's say, momentum conservation law that was obtained in free space is modified due to the appearance of two phenomena here. One is the fact that we are in a solid, so actual momentum is not conserved, and we need to consider that the role of momentum for a free electron is assumed by the crystal momentum for a block electron. So due to that, here we have the combination of crystal momenta and actual momenta. The second point is that if we use the first Brillouin zone as a group of wave vectors that may help us to index all the possible electrons in the system, then if in this conservation law the final value is out of the first Brillouin zone, then we need to consider also a translation so that the final result is taken back into the first zone. Considering this equation, for the moment, I kindly ask you to, let's say, accept the motivation of the appearance of this additional H bar G just using this qualitative indication that I have just given to you. Then, let's say, the real motivation of the presence of this additional vector here in the equation of conservation is due to a symmetry of the Hamiltonian. So this vector here appears due to a symmetry of the full Hamiltonian of the system, where with full Hamiltonian of the system, I indicate the Hamiltonian where we have both the electrons, the contribution to the energy given by the electrons, and also the contribution to the energy given by the ions. But as for the moment, we have not yet considered the contribution of the ions in the Hamiltonian. For the moment, I just give you this result, and then I will comment again about this equation when I will present you also the ionic contribution to the total energy of the system. So for the moment, I kindly ask you to keep this equation for granted, just with the qualitative indication that I have just given to you. But I will comment again on this equation later when I will consider again the contribution of the ions. So for the moment, let's just accept that the motivation of that is just due to the fact that we want to use only one zone for the representation of the crystal or the wave vectors of the electrons. So in this case, when we consider electron and photon interaction, again, we have just these two equations. And just one comment concerning these equations. This equation enables us to discuss about the interaction of the electron and the photon. So we consider the interaction, not the, let's say, wave-like interaction that was discussed, for instance, by Drude, but the interaction between the photons, so not the wave interaction as discussed before. Because I don't consider that as during the last lesson, we saw that it's possible to, let's say, rewrite an equation considering conductivity that is very similar to the equation that I wrote to you when we considered the Drude model, just by rescaling the value of the effective mass of the electron. So in general, if the system is, let's say, isotropic, then you may expand the expression of the energy and find that the only effect of the band structure of the system is just to rescale the actual mass of the electron. So the idea is that for what concerns the interaction between the electron and the electromagnetic waves, the picture is quite close to the picture that we have obtained both in the Drude case and in the Sommerfeld case, apart from the, again, slight change in the parameters that describe the electron. So the overall structure of the let's say, optical properties, dielectric constant, just due to the to that kind of formalism, is maybe similar to the one that we have already observed before. The main difference here is the difference due to the fact that we may also discuss this kind of interaction. So we may consider the actual absorption of a photon by the electrons, so the capability of the photon to jump from one level to another level. And at the end of the discussion, we will always also see why this mechanism was not possible in the case we consider just the Sommerfeld picture. So to try to solve these equations, let's just consider this contribution. So let's just consider the intensity of that term. Q is associated to the photon, so is equal to 2 pi over lambda. But if we consider the interaction between the electrons and the electromagnetic waves in the visible range, then what we have is that lambda is in the range 400 nanometers, 700 nanometers, more or less, if we just consider visible light. Differently, K, let's say at the moment we do not know the actual value of K, but K is of the order of, let's say, pi divided by A. So pi divided by A is the border of the zone. So that is, let's say, a typical value that may be associated to the wave vector of the electron or of the block electron. And in this case, A is of the order of some angstroms. So due to this consideration, we have that the wave vector of the photon, sorry, is very, very small with respect to the typical wave vector of the electron, because you have at least 3 orders of magnitude between the wavelength of the photon and the typical scale of the lattice spacing. So due to that, Q is very, very small with respect to the initial electron wave vector. So due to that, if we rewrite this equation considering this relationship between the photon wave vector and the electron wave vector, then what I have just discussed to you before, so the possibility to have a final value of the wave vector that is out of the first Brillouin zone is impossible to be observed, because this vector Q that I presented here in this diagram is very, very, very small. So even if given the initial value of K, the final value of K prime, will be very, very close to the initial value of K. So from the point of view of the contribution of the photon to the variation of the wave vector of the electron, that contribution is negligible. So we do not need to consider the contribution of G, because K prime will be never out of the first Brillouin zone due to the small intensity of Q. So we have that H bar K prime can be considered to, sorry, that is not a derivative, it's just the value of the wave vector of the electron after the interaction will be nearly equal to the initial value. So from the point of view of the change in the wave vector of the electron, no change is expected when we consider the interaction with the photon. A different comment has to be applied to the first equation. So if we consider the energy conservation equation, I just rewrite that here. what we have is that we know that K prime will be equal to K. So this is E n prime, the final value of the energy of K, is equal to the initial value of the energy evaluated at the same value of the wave vector plus the energy of the photon. For visible photons, so photons that belong to the visible part of the electromagnetic spectrum, then this energy is in the range in between 2 and 4 eV. So the idea is that in this case, for what concerns the energy conservation, the value of the energy of the photon is comparable with the value of the energy of the electron. So in this case, we may not neglect the contribution of the energy of the photon when we consider the change in energy of the electron. So from the point of view of the, let's say, of the contribution of those two equations, so the conservation of energy and conservation of wave vector of crystal momentum, then what we have is that the wave vector of the electron is nearly unchanged, and the only term that changes is the energy. The change in energy depends on the electronic band structure of the electron. And if we consider the, let's say, typical diagram that we have observed for, let's say, nearly free electrons, in that case, we had something like this. So one band, second band, and so on. So just to make an example, if we have that the Fermi energy is here, for instance, then we have that, just to make an example, all the levels that are found in this area, in this region, are occupied levels. So here we have electrons, and all the other levels are unoccupied. So for instance, what we may observe is that if you pick up one electron here, then due to the absorption of a photon, the initial level of the electron may be, for instance, the one here, this one here, then the final level will correspond to the same value of the wave vector. So the final level is on the let's say, is lies on the same vertical axis that goes through the initial level of the electron, and the difference in energy between the initial level and the final level is equal to the energy of the photon. So in this case, we have an occupied level here. So here we have an electron that may absorb the energy of the photon, and then we have a final level that is empty. So we have the opportunity to observe this kind of interaction. So the idea is that depending on the specific electronic band structure of the solid, in case we have the opportunity to make transitions like this one here, and also in case this difference in energy belongs to the visible light spectrum, then what we may expect to observe is the fact that the system display an absorption corresponding to a specific energy, so to a specific wavelength. And if we have an absorption at a specific wavelength, then what we may expect to observe is the appearance of a color, because at this point we have just a localized absorption. So some part of the electromagnetic spectrum can be absorbed by the metal, some other parts are not. So what you expect is that the that solid will not display the typical shining and bright, let's say, metallic-like behavior of, for instance, aluminum, but may have the opportunity to display a color. And just to make an example, in the case of copper, there is the opportunity to have an absorption like this one here in the red part of the spectrum. So you have an absorption that is of the order, you have an absorption energy that, due to the electronic band structure of copper, is of the order of, if I remember correctly, 2 eV. That part is in the reddish part of the spectrum. So you have a strong contribution of the dielectric constant of the system in that part of the spectrum. And due to that, you have this, let's say, reddish color of copper. And the same is found for gold. So also in the case of gold, due to the electronic band structure of that metal, you have the opportunity to observe a transition in the visible part of the spectrum. And due to that transition, you have the yellowish color of gold. And as the structure of the noble metal, as the electronic structure of the noble metals is similar, so you have that the D levels gets occupied, and you have just one S level that is half filled. Then one would expect that also silver would display a color, because again, copper and gold are colored. But in the case of silver, you have that this transition is in the UV range. So due to the fact that that transition for silver is out of the visible part of the spectrum, then silver displays no color in the visible light range. But in principle, also for silver, it is possible to observe this kind of transition. But here we have just the problem of frequency. So the frequency may not be detected by our eye. So due to that, we observe no color in this metal. And if you observe this this diagram here, so the diagram discussing the energy band structure of a nearly free electron-like metal, what we observe is that apart from the actual structure of the energy versus K dependence, the main feature that we have here that we had not in the case of the Sommerfeld model is the capability to have many different bands, one above the other in this diagram. And this opportunity is given by the periodicity of the energy versus wave vector function. So in the case of block electrons, due to the periodicity, we have many bands that are indexed by the n index. Here we have n equal to 1, then we have n equal to 2, 3, 4, 5, and so on. So due to this fact, we have the opportunity to observe, we have the opportunity to have taking into consideration this requirement. So the fact that in the case we consider the interaction between one electron and the photon, the final value of the electron wave vector will be nearly equal to the initial value of the electron wave vector. So this is a sort of interaction where the wave vector of the electron may be considered to be fixed. So in this picture, we have the opportunity to have different electronic levels that correspond to the same value of the wave vector. Differently, in the Sommerfeld case, we had not this opportunity, because if you fix the value of k, then just one level corresponding to that value of k. So there was no opportunity to observe any transition from an initial value to a final value. So sorry, from an initial level to a final level due to the absorption of a photon. So in that case, even if we had let's say, the electronic levels at disposal, it was not possible to fulfill these conservation laws, so to observe the actual absorption of a photon. Here, thanks to the appearance of, again, different many levels corresponding to the same value of the wave vector, thanks to the periodicity of a problem, the case also the absorption of single photons can be a feature of the system, and one of the consequences of that, again, may be the appearance of the color of the metal. So in this case, the appearance of a color in a metal can be traced back to the specific electronic band structure of that metals. So each time we have the opportunity to observe a transition like this, then we have the appearance of a color. In principle, let's say the electronic band structure of a system is more complicated than this one here. So in many situations, you have also the opportunity to have a transition from an occupied levels below EF up to a free level at EF. Using this diagram, this phenomenon cannot be observed, but in general, you may observe that as, again, the band structure of the system in general is more complicated than this simple parabola that I have plotted here. So let's say the conclusion is that the appearance of color is a consequence of the behavior of block electrons, or to be more precise, of the periodic structure of the energy of the block electrons. Okay, that was, in this case, I wanted to give you just a qualitative indication of this effect. So due to that, I just made this discussion concerning this simple electronic band structure, and referring to just to these two equations. Again, as I told you before, I will comment again on this second equation when we will discuss the properties, the contribution to the Hamiltonian coming from the ions. So with this last topic, I would like to conclude the part that was related to the description of the properties of the solid when we consider the presence of the periodic ionic potential in the Hamiltonian of in the Schrödinger equation. So what we have observed up to now is that just considering block electrons, so only considering the contribution of the periodic so just considering the fact that in the Hamiltonian we have an actual value for the interaction potential between the electrons and, for instance, the ions, then many properties that were not considered up to the Sommerfeld model now appear. So we have again the periodic band structure of the system. Then, so we have this periodic band structure. And then and so all the details, all the structure concerning the actual shape of the Fermi surface. So as we saw, there is the opportunity to So the Fermi surface may interact with Bragg planes, and the interaction between the Fermi surface and Bragg planes induces a deformation of the Fermi surface. And so due to that, we notice that for some metals, the actual shape of the Fermi surface may be quite different from a sphere. So in this case, we have also distortion. We may observe a distortion in the Fermi surface that may have an effect on the electronic properties of the system. Then what we also studied was the effect of the effect of the external fields over the behavior of the electron. And we did that using the semi-classical equations, where semi-classical was meant to indicate that the let's say during the motion of the electron, we have two kinds of forces. Let's say one kind of forces is represented by the external forces, so electric field, magnetic field, electromagnetic waves that are applied from the outside to the solid, whose scale can be considered very large with respect to the, let's say, size of the electron, or with respect to the de Broglie wavelength of the electron. On the other side, we have the forces due to the lattice, and in that case, the scale of variation of those forces is of the order of the lattice spacing. So those forces may not be handled classically, but has to be handled quantum mechanically. And the effect of those is, let's say, described by the presence of the actual interaction potential between the ions and the electrons. So in this case, semi means the external forces are considered as classical forces, so are handled classically, but the quantum mechanical ones are handled through the energy versus wave vector dependence for the electronic system. And in this case, the important point is that the role of what was the momentum in empty space is now given to the crystal momentum of the electron. So the crystal momentum has the role of what was, again, a momentum in classical dynamics, and due to that, the crystal momentum of the electron, in particular the derivative of that, appears in what is the equivalent of the second law of dynamics for the semi-classical equations. And in this case, we apply those equations to the presence of the electric field, magnetic field, electric field and magnetic field orthogonal with each other. And in these cases, somehow we obtained what was obtained by, let's say, classical mechanics, but also new phenomena such as the possibility to have positive, negative values for the Hall coefficient, the possibility to observe the magnetoresistance, and everything is due to the fact that the shape of these main results are due to the fact that with respect to the, let's say, typical electronic orbits that for spherical Fermi surfaces are circles, in the case of a magnetic field, for instance, can now be more, let's say, those typical trajectories may now be different from a typical circle due to the presence of what we observe, in particular by discussing the Hall effect and magnetoresistance, also by the presence of open orbits within the system. So now the system displays a dynamics that is more variable, more rich with respect to the typical dynamics of the, for instance, Sommerfeld model. So all those details were just, let's say, accessed just by including the contribution of the ionic lattice into the Schrödinger equation. So the starting point was the removal of this hypothesis. So one of the hypotheses that were used by both Drude and Sommerfeld was the free electron approximation. In this case, we have observed that just by removing this requirement, many details can be obtained for what concerns the dynamics of the system, and many features of in particular of the metals that were observed experimentally but were not explained from the theory, can now be explained and discussed just by considering the contribution of block electrons. So, sorry, block electrons, by the contribution of the lattice. Now, we have up to now, from the beginning of the lessons, we have always used another hypothesis, that is the independent electron approximation. So for the moment, we have used also this hypothesis. So in the equations, we just write the wave function of one electron. We do not consider interaction of that electron with all the other electrons. I open a parenthesis. In principle, this is not actually true, since when we consider the pseudo-potential approach and the OPW method for the evaluation of the electronic band structure, we actually included some sort of interaction between the conduction electrons with the core electrons. So specifically in that point, the sort of electron-electron interaction was considered, but that interaction was not, let's say, was introduced considering the pseudo-potential, but was not included from the beginning in the equations. So that was a sort of interaction between independent electrons. So the first approximation of the wave function came from the independent electron approach through the tight binding model, and that later that approach was used to, let's say, discuss this sort of electron-electron interaction. So from now in the next lessons, what I would like to discuss is this second hypothesis. In particular, I would like to discuss with you about what happens if we remove also this second hypothesis. So if we consider the interaction So what happens if we consider the interaction among all the electrons that can be found within the system? This is, let's say, the removal of the free electron approximation changes the Hamiltonian from the, let's say, purely kinetic that we had for the free electron approximation. So this was the Hamiltonian for the free electron, that was modified into the an Hamiltonian where we have again the kinetic term plus an additional term that is the potential term. So this is, let's say, the complication here is due to the appearance of this U that has just one symmetry, and the symmetry is the periodicity. So what we know is U of R is periodical. So let's say the Hamiltonian changes, but the structure of the Hamiltonian is nearly the same. Or with structure of the Hamiltonian, I mean the fact that this is a one-body problem, and this is, again, one-body problem. So what you are discussing here is, what we are trying to do here is to evaluate the electronic wave function when you consider a single electron problem. The single electron problem may be the free electron one or the block electron one. But in both cases, you just consider one electron. So the complication is just due to the addition of this term. In case you consider the, in case you remove the independent electron as approximation, then you have many more problems from the mathematical point of view. First problem is the electronic wave function may not be a wave function in the sense that we have discussed up to now. So if we consider now a wave function of the n-electron system, then you need to consider a wave function that depends on not just on one variable, but on the variables of all the electrons in the system. So in this case, you need to, let's say, make considerations or assumptions regarding not a one electron wave function, but a many electrons wave function. So you need to consider here the dependence on the coordinates of all the electrons. And then you have also that the Hamiltonian, from this point of view, has to be the Hamiltonian of all the electrons. So you need to consider a Schrödinger equation when you consider the summation of so you have the summation of the kinetic terms of all the electrons, then you have the summation of the contribution coming from the interaction between the electron and all the possible ions. So in this case, you also have a summation over, for me, but it's better to write that in the Colombian form, so it's easier to understand that. Yeah. So here we need to consider the sum over all the electrons from 1 to n, and the sum over all possible ions of the, for instance, so you have the Colombian term due to all the ions, and in this case, the charge is minus Ze, sorry, plus Ze minus E. So you have the minus charge of the electron and the plus charge of the ion. And then there's also, so this is, again, similar to the contribution that we have observed up to now. And then what we need to consider is also the fact that we need also to consider the contribution of the electron-electron interaction due to the Colombian potential. And in this case, we have also a 1/2 in front of this summation to avoid the double counting in case you include I and J, and then you exchange the labels and you have J and I. So this 1/2 here is just to avoid the double counting of I and J when you invert the value of I and J. So now the Hamiltonian is more complex because we also need to consider the interaction of all the electrons with each other. So the fact that here we have n coordinates, and the fact that here we have the interaction between all the possible electrons in the system makes the solution of the problem when we remove the independent electron approximation very hard from the mathematical point of view. So in this case, the idea is to try to simplify the system, to try to simplify in particular the Hamiltonian of the system, so that this will display a structure that is similar to the one-body Hamiltonian that was used in the block problem, so to simplify the mathematical side of those equations. In this case, I will present you two approaches. One approach is the R3. The second approach is the R3 Fock that is based on this later determinant. So these are two possible solutions for what concerns the solution of the Hamiltonian and the, let's say, also to find an expression for the electronic wave function when we have to consider an actual wave function that depends on all the coordinates of all the possible electrons. So these two methods follow, let's say, on one side there are some similarities between the two, on the other side there are also some differences. So I will start with the R3 one, that is the simplest one, and then I will introduce some complication. You know, actually is not an actual, just a complication, but is the consideration of the actual properties of the electrons that are fermions. And regarding the R3 Fock method, I will share with you let's say a document, since in the textbook the contribution of this later determinant is not discussed in detail. I will give you another document where you find the discussion that we'll present to you concerning this later determinant. So in this case, I will include that in the classroom after the lesson. So first step is the discussion of the R3 model. Okay, since it is 6 after 10, if for you is fine, I will make a presentation of the hypothesis of this model, and then the actual calculation, if for you is fine, I will do that after the break. So the first thing I would like to introduce you is what are the hypotheses of the R3 model? The idea of the R3 model is to transform the n-body problem into a one-body problem. So the idea is to simplify the structure of the Hamiltonian, so to reduce the mathematical complexity of the Schrödinger equation, and to bring that to be equivalent to the complexity that was found in the free electron approximation. So where does the main complication comes from in the Hamiltonian? The Hamiltonian, we have the kinetic term, and if you note, I will rewrite that here. So the kinetic term is just equal to the kinetic term that we had in the, let's say, we have seen up to now. The only difference is the fact that we have a summation, but the structure of this term here is again equivalent to what we had before. We just need to consider the same term applied to all the electrons. So the starting point is always the same. Then we have also another if you don't mind, I just write here U over I, because the idea is to focus on the fact that also the potential term is a term that depends on the coordinate of just one electron. So I write the interaction potential with the ions in this using this structure just to stress the fact that also this term involves just the coordinate of one electron, not of many electrons, just of one electron. The real problem is the third term, where we have a summation over I and j, and in this case we have so this is the real problem, because this term cannot be written as a function just of the coordinate of one electron. Here we need to consider the coordinates of at least two electrons. So this is the real point that prevents us from using a simple Hamiltonian. So this cannot be written as a sum of single electron Hamiltonians. So you may not write that just due to the presence of this term. So the idea of R3 was the following. Instead of considering the interaction between one electron and all the other electrons as a two-body interaction, so this electron, so electron I with electron J, and J runs over all the possible electrons, the idea was to consider the contribution of all the other electrons as an average contribution. So Hartley decided to restate the problem from let's discuss the interaction between any two electrons belonging to the system to let's discuss the interaction between one electron in the system and the average density charge that is due to all the other electrons. So at this point, the problem is how I may handle the average density charge that is due to all the other electrons. In this case, you may associate to one electron, the electron with index I, a density charge that is minus E times the square of the electronic wave function of that electron. So in this case, you may write down the total density charge of the electronic system as minus C and a summation over, sorry, please, not here, please, I try to cancel that. Is here I was discussing the density, the charge density at the position equal to R. So here I decide the index is not on the position, but is on the level. So please here remove the index I from the position and place that on the level corresponding to that electron. So in this case, we have that the actual So due to the fact that I fixed the position, I just included the contribution in that specific position that is given by the charge density associated to all the possible electronic wave functions in the system. So please note that here, if I write this equation and this equation, I'm assuming that I've already solved the let's say, one electron problem in the free electron approximation. So I am assuming that I have already at disposal a set of electronic wave functions that may be used both for the evaluation of the density charge of one electron and also for the evaluation of the density charge of all given by all the electrons. So if we have this, so if we have the density charge given by the all the possible electrons, we may write the potential term, the equivalent of this, by using this expression. So we have the interaction between the Coulombian interaction between the charge minus C of one electron, and that is the interaction between the electron in position R and the charge density that is in, sorry. So the interaction between the electron that is in position so we have the interaction between this charge density that was the total charge density, position R prime, with the electron that is in position equal to R. So in this case, if you notice, to evaluate this, you just need the, this is just a term that is similar to a, let's say, a term that depends on the coordinate of just one electron. And the coordinate in this case is just the R coordinate, because you make an integral over R prime, and the, let's say, complexity of the system is included into the definition of this effective charge density that comes from here. So using this approach, you have the situation where the Hamiltonian can be, sorry, where the potential term that is due to the interaction between one electrons and all the other electrons is replaced by a problem where you, let's say, include this the contribution of all the electrons into this total charge density. And just a comment on the index I here. In principle, if you discuss the interaction of one electron with all the other electrons, in principle, if the index of that electrons is, for instance, given by, I don't know, K, then you should write that this summation is over I that runs from 1 to n, but with I different from K, because in principle, K is the electron that you want to make interact with all the other electrons. But due to the fact that the number of electrons that you have in the system is of the order of 10 to the 28 in macroscopic systems, then in general, the contribution of 1 over 10 to the 28 is generally neglected. So here you do not make any constraint concerning the index of summation. So due to that, you do not discuss, please consider only the electrons that are different from K, because again, you consider just a huge number of electrons. So you expect that the, let's say, this additional self-interaction that you include in the system will not change things due to the fact that is just a negligible contribution, considering the fact that you have a huge number of electrons. So thanks to this effective, effective interaction between the electron and all the other electrons, you may rewrite, so using the total charge density, we have that the initial Hamiltonian can be written as a sum of kinetic term Then we have I write also up here ions to highlight the fact that this is the term that comes from the ions. And then we may also write UL of Re. So in this case, the electron term depends also on the coordinate of one electron, because you have somehow fixed the configuration of all the other electrons and you have included those into the total density. So this is a strong contribution to the mathematical complexity of a problem, because in this approximation, it is possible to rewrite the initial Hamiltonian that was an n-body problem into the sum of one-body problems. So this was an n-body problem. Here you have a sum so from an n-body problem, so strong interconnection between the coordinates of all the electrons, we switch to a many one-body problems. So many problems that are equivalent with each other due to the fact that each of those problems refer to the coordinate of one specific electrons. But in the structure of this problem, then we have that, again, just the coordinate of one electron appears in each of those one-body problems. So after the break, I will discuss what is the effect of that on the structure of the electronic wave function, and so how that gives us the opportunity to strongly simplify the very complicated structure of the n-electron wave function. Okay, so I stop the registration.